welcome back to Isifundi Training and the second week of our 2024 Bite-Sized Corrosion Summer School, where we're talking about cathodic protection in hazardous environments as we explore some of the cathodic protection design considerations in tank farms and other hazardous installations. Now, last week, we started our 6 weeks discussion looking at cathodic protection in hazardous environments. And we looked at what we term hazardous, and we started exploring some of the challenges we need to consider when we're thinking about implementing a cathodic protection system. We also considered some of those challenges which may even exist if we already have CP installed on the tank farm or the depot or the refinery. So we spent a long time talking about electrical isolation, surge protection, cathodic protection, earthing, and we even touched on some of the discussions that we were going to talk about today that are facing the design engineer. So my guest, Neil Webb, and I are going to continue this discussion today, and we're turning our attention to the actual design of cathodic protection systems. So welcome back, Neil, and thank you for joining us. It's lovely to see that you're able to, even though you're in the bush.
I'm sitting at Kruger Park Lodge, and it was searingly hot yesterday and distinctly chilly today, but we'll keep the temperature up with some lively discussion, I hope.
Last time we spoke about some of the challenges of designing a CP system under the constraints of the hazardous environment. And before we address these unique challenges, surely just designing CP for a tank is already a bit of a challenge?
Yes, for sure. I mean, one of the analogies that I like to draw in terms of cathodic protection in general is that cathodic protection is like the sun. And if you cannot see the sun, then you're in the shadow. And equally with cathodic protection, if you consider yourself to be a surface under cathodic protection, if you can't see the anode, you're in the shadow. You're not necessarily going to get protection. And of course, that's not an absolute situation. You know, you just the way you get reflected light off clouds and overcast like it is at the moment. You also get protection from remote anodes where you get the current distributed through what we call remote earth. But in general, when you're dealing with a tank is a fairly large surface. It's not a plane, well, it might be a planar surface if it's at the bottom of an above ground storage tank. Or if it's a buried tank, it's looking to be protected from all sides. And it's quite difficult to illuminate. If you think about using your cathodic protection as a light source, try and illuminate the entire surface of a tank with a single light source. It's almost impossible. And so from that point of view, it is more difficult to provide cathodic protection in these crowded spaces. And in fact, there is a specific standard, British standard, that deals with cathodic protection in congested environments, where they talk about cathodic protection in congested areas and networks and things like that. And tank farms, in many ways, are like a network.
Yeah, so Neil, now, if we're talking specifically about cathodic protection and cathodic protection design, I think we're all now very familiar that we need some anodes and a rectifier. So if I'm thinking about a pipeline, we often prefer to have a remote anode distant from the pipe to cover a greater area. And in a tank farm, or as you say, these congested spaces, these crowded areas, can we use remote anodes? And I mean, on a pipeline that's 100 meters kind of distance from the pipeline, what would be remote on a tank farm?
Well, the same criterion applies in a tank farm in terms of being remote, in that the remote indicates that you're far enough, that your anode is far enough away, that the object being protected does not fall inside the potential gradient of the anode. But one of the challenges is, you know, if you've got a refinery or a tank farm or a depot or whatever, it's a fairly small area. You don't want to go 100 meters away, which might be, you know, two properties away in the case of a depot, and stick an anode in the ground, because you're going to interfere with everybody else in the vicinity. On a big refinery, it's hardly possible to get remote by going away horizontally. However, one of the things that you can do, and this depends very much on the geology of the location, is you can go deep. So if you think about dropping the source of current down into the earth and shining the light upwards like a floodlight from underneath, you can get to see a significant area of the installation. And so by putting your anodes vertically at some distance below the surface of the earth, you can achieve remoteness, provided you have got conductive geological strata in between the location of the anode and the surface. So if you've got a refinery that is built on rock, you can't use deep anode because you can't get current through the rock.
Okay, so sometimes we talk about tank farms and we talk about using distributed anodes, and then that just goes counter against everything you've said about being outside of the potential gradient of the anode. So let's just look at that a little bit.
No, sure. And you're quite right. It is diametrically opposite to the concept of remote Earth. And in this case, we actually deliberately place the anodes close to the object that we want to protect in order to ensure that the surface is actually inside the potential gradient of the anode. And that then allows you to deliver current preferentially to the object that you want to protect. Because it is now inside the potential gradient, it has the benefit of the higher driving potential associated with that gradient, and therefore the current will flow preferentially to that surface. And that is one of the ways that we get around the challenge sometimes of infrastructure which is cast into concrete. For example, even in big refineries, for example, you have cooling water systems which go into the foundations of cooling towers and things like that, pump stations, and so on. And these pipes, which are buried, may then be incorporated into these civil structures, and you can compensate for the loss of current to those structures by placing the anodes close to the pipe or the tank or whatever it is. And then you'll end up preferentially protecting that area, as I've said. However, now you have the situation of only protecting a relatively limited area with a single anode. And therefore, you now need to increase the number of anodes. And that is why it's called a distributed anode system, because we now place a large number of anodes around the structure or along the structure if it's a buried pipe, so that each anode protects a specific small area and you don't lose current elsewhere. The net result of that is that your anode system actually has a far greater capacity from a current point of view than is required for the installation, but you need those anodes from a distribution point of view so that you get a nice uniform potential gradient set up around the structure that you want to protect.
Now, that might hark back a little bit to our discussion last week about electrical isolation. If you are deliberately protecting infrastructure within the potential gradient, then I'm guessing that you are less concerned, or you've taken into account the current that you're going to lose if there isn't an isolating flange that has been installed. Would that be a fair reflection?
Yes, very definitely. And in fact, we use that principle quite extensively now. And rather than endeavoring to isolate the tank, we link it to everything and compensate for the loss of current by reducing the loss. Say in a remote anode situation, the current will go everywhere, every single place that it has been connected to. So to limit that spread, we put in isolation. If, however, you bring the anodes close to the structure, you now, as we've said, you get the preferential current flow to the structure. And even though current can leak out through the breakout piping or the earthing system or whatever it is, the extent of loss is significantly reduced.
Yeah, I think you may have in part addressed this, but when we think about these hazardous environments, which we've described as tank farms and refineries and depots primarily, when we're looking at a single AST, above ground storage tank, and we're trying to protect its base, one anode won't cut it. So you said we're going to use a couple. Would they be strategically located around the base? And that whole base should be bare. That's quite a large surface area.
Yeah, for sure. I mean, if you take, even a relatively small tank, like about 30 meters diameter, that's got a surface area of 700 square meters. And if that's bare steel, that's now a fairly high current demand.
Yes.
So the anode system that you install to protect that tank base typically would either be a continuous wire anode buried in a ring around the base that's relatively shallow. And whether or not you get full protection to the center of the base is questionable. But the systems that I've seen where it's been installed, we haven't yet had reported failure of the tank due to corrosion at the base in the center. The advantage of a bare tank base, of course, is that you don't need to worry about overprotection because you haven't got a coating to blow off. So you can push the current and the driving potential somewhat harder than you would under a coated pipeline situation in order to try and get protection to the center. The next best thing is to, instead of putting in a ring fairly shallow, is you drive the anodes down deeper. As I've said, ideally you need to have geology that is suited to that. In other words, conductive strata below the tank. And if you push the anodes down, then you get the 120-degree cone from each anode. And by working out what the geometry of the situation is, you can then effectively protect the entire tank base with a situation like that. And that is one of the best ways of retrofitting a system to an existing AST installation.
Right. Now, you made a passing comment, which I want to hone in on a little bit. You said the tank bottoms are generally bare, and so we can drive this quite high and we're not going to blow off a coating. So I'm going to throw back at you and say, okay, what if I've got a coated tank? What are we going to do?
Well, if you've got a coated tank, then you need to be somewhat more circumspect in terms of gradients. And you would then look at putting in the distributed anodes relatively close to the tank so that you can maintain a fairly tight control over the potentials of the actual tank itself. One of the things we need to remember is that with an above ground storage tank, the chances of that tank base being coated are, well, I can't say that there's absolutely no chance, but I have in fact yet to hear of anybody coating the underside of a tank base, other than perhaps with a holding primer to prevent it from flash rusting during construction.
So
we're not talking about the inside of the tank. That's a completely different story.
No. And the cathodic protection we're talking about is for the stuff that is in contact with the ground, not dealing with the contents of any of these tanks.
Yeah.
Now, Neil, another challenge that is often raised as a red flag.
Right.
We spoke about earthing being a problem, something we need to take into account last time. If I think back to the basics of design, the amount of current we need is going to be determined by the surface area. What about this plant earthing? How significant is that? How many more anodes am I going to need? Is it cost effective to still do a CP system if I'm not isolating from my earthing? How can we manage that? How does that impact the size and the quantity of anodes that we're going to be using?
Well, the impact of earthing is less than one would expect. And sometimes you actually need to wonder why people bother with earthing. If you've got a bare tank base in contact with the earth, and it's got an area of tens or hundreds of square meters, what's the point of putting in a 1 square meter earth rod? Except, of course, that they put in many earth rods. So the bottom line, of course, is that the surface area of the earthing system is relatively insignificant compared to the surface area of the tank base itself or a bare tank. If you have a coated tank, it's a lot more significant, the relative area of the bare copper compared to the exposed area of the steel due to defects in the coating.
Degradation, yeah.
But remember also that when we do these distributed anodes for coated surfaces, the installed capacity is far greater than the current requirement because of the distribution.
Yeah.
And so therefore there's usually ample capacity to take care of the additional surface area of the earthing.
Right. Okay. Well, thank you for that. And a sort of allied question. We know that on pipelines, sacrificial anodes are definitely more in favor than impressed current systems, largely driven by vandalism challenges. And we know that in tank farms, usually there's greater security and less risk of losing the rectifier. But can we use sacrificial anodes in a tank farm? And I'm sort of going to part answer that and say, if we're talking about these big surface areas, maybe it's not very practical.
Yeah, you've pretty much answered your own question. Because of the surface area and the current demand, sacrificial anodes generally are not satisfactory. They're not the right solution. If you look at the possibility of using, for example, a sacrificial anode system to protect the underside of a bare storage tank, you would have to put in almost a continuous cast bed of sacrificial anode in order to provide the current.
Right.
It's just totally impractical.
Just a non-starter.
But,
okay, so
but
in theory it could be done, but practice is just not there.
Well, I don't know that if it can even be done in theory. I mean, when you
Right.
actually work out the quantities required, it's not even possible to physically put enough anode material in the ground in order to work.
Okay.
Where sacrificial anodes can work is in fire water systems. And this does depend on the overall design of the tank farm or the installation. And I suppose primarily we're talking about small installations like depots and things like that, where the fire water system may be relatively remote from the tanks and therefore somewhat of a challenge to incorporate into a regional or distributed anode CP system. You can then install sacrificial anodes. For example, if you have a plastic fire water main with coated steel risers, manifolds, hydrants, and things like that, you can protect those risers and manifolds using sacrificial anodes. And we have, in fact, done that on a couple of situations where the fire main is plastic. If the fire main is steel, then it's probably easier to incorporate the fire main into the overall impressed current system.
And of course, as we mentioned, I think as we started the series, that having your fire water system not functioning as a garden sprinkler system is absolutely critical in these installations, because that is your first defense when there is a problem. So taking the protection of your fire water system seriously is something that sometimes slips the bandwagon a little bit. And sometimes I think even the location of fire water systems is not always known. So maybe we should take a closer walk around the installation and just verify that we've picked up all of the hydrants and that they are protected, because they are so critical from a safety perspective.
For sure. And it is something that is way more important, I think, in smaller installations, things like depots and, well, depots in particular. We do quite a lot of maintenance work in depots, and it is actually quite frightening how little many of the depot managers and operators know about their own system. They don't know whether the fire main is steel or plastic. In fact, sometimes, as you've said, they don't even know where the fire main runs under the ground. They don't have drawings. They don't have operating manuals and operating systems. And that's an indictment against many operators, unfortunately.
Oh my goodness, Neil, we are almost out of time. And I have a number of questions which I'm going to hold over for tomorrow, but you can start thinking about them. We will be looking at some of the risks associated or that we might encounter, let me put it that way, during the design and installation. And I'd like us to specifically talk about cathodic protection where we have secondary containment. So if you can put your thinking cap on, and we'll address that tomorrow.
That's not an insurmountable problem, although it's a nice challenge.
And of course, we also haven't spoken about what the impact is of the base that the tank is on, whether it's directly on the soil or if it's on concrete, and how that impacts the cathodic protection design. So maybe we can touch on that tomorrow as well. So forewarned, there's forearmed, and I've given you a heads up. And just a reminder that it is so important to remember that our cathodic protection system design is very site specific and very circumstance specific, and really shouldn't just be, if we can say, the bottom drawer design, the last one that got used seemed to work well, we'll try and roll it out again. So I encourage you to take that into consideration. Goodbye.